Okay, our next section of college algebra is chapter 4.2, where we've just gotten done doing the exponential function, and now we're going to head into something called the logarithmic function. And basically, I want you to think back to last chapter when we were finding the inverse of things. Remember how we found the inverse of a function? We replaced x with y with x, and solved for y. We said the domains and everything were switched, right? The domain of one function was the range of the inverse. The range of their function is the domain of the inverse, but it was just the reverse. So we graphed both on the same coordinate system, and this is what we had. We have this nice symmetrical graph about the line y equals x. Okay, we had 1/2 x cubed minus 4. The inverse of that was the cubed root of 2x plus 8. Okay, notice both graphs are symmetrical about the line y equals x. That's what we did last chapter. Well, every function that's 1-to-1 has an inverse, right? So these two were 1-to-1. They had the inverse. And remember how the x and y's were reversed. If I put 2 in for x here, 2 cubed is 8. Half of 8 is 4. 4 minus 4 was 0. If I put 0 in here, 2 times 0 is 0, plus 8 is 8. Cubed root of 8 was 2. We're always reversed like this, right? If I put 0 in for x, I got -4. If I put -4 in for x in its inverse, I got -8 plus 8 is 0. Okay, they're always reversed. -2 cubed is -8. Half of -8 is -4. Minus 4 is -8. -8 times 2 is -16. Plus 8 is -8. Cubed root of -8 is -2. Okay, so we always have this situation happening, right? We had that. We're done. Now, therefore, we should be able to find the inverse of y equals 2 to the x. We know how to graph it. When x is 0, 2 to the 0 is 1. When x is 1, we get 2. When x is 2, 2 squared is 4. When x is 3, 2 to the third is 8. 8. Okay, when x is -1, 2 to the -1 is a half. When x is -2, 2 to the -2 is 1/4. Right? We had a horizontal asymptote. It never actually touches 0. And then shoots off here exponentially, right? We know that our horizontal asymptote is y equals 0. Okay, there's y equals 2 to the x. Well, we're supposed to find the inverse. So x equals 2 to the y. How do I solve for y? We don't have something. What am I going to do? Take the y root, I guess, or of 2. I don't have anything to do here, but I can reverse the x's and y's at least and get an idea what that would look like. Okay, I know what y equals 2 to the x looks like. We just plotted those points, 0, 1. 1 gives me 2, 2 gives me 4, 3 gives me 8. So what's that look like reversed? Let's see. Well, it'd be 1, 0. It would be 2, 1. It would be 8, 3. It would be, what else did we have here, gang? In the original one, when x was -1, what do we have, a half? So it'd be a half -1. We had, when we put -2 in, we got a fourth, so it would be a fourth -2. So that kind of makes sense, doesn't it? Because if I would graph y equals 1, the inverses should be reflected upon. Yeah, that looks good. So x equals 2 to the y, we can graph it, but we couldn't write it as a function. I want to write y equals something. Okay, and so we defined it as y equals log base 2 of x. Okay, it's the inverse of a to the y equals x. Okay, or I'm sorry, it's the inverse of a to the x equals y. All right. So since we couldn't take the x equals 2 to the y and solve that for y, they invented something called the logarithm, which means exponent. Okay. So we're saying that y is the exponent you put on this base to get x. Okay. Another way of saying y equals log base a of x is a to the y equals x. Those are the exact same thing. Okay. So I'm going to say, back to my problem, the inverse is y equals log base 2 of x, which is the exact same thing as saying 2 to the y equals x. Okay, but because I couldn't solve this for y, we invented this little word logarithm, okay, to be this situation. All right, so the definition, again, this is what I want you to be able to do, is go back and forth between log form and exponential form. We're going to have to be able to go back and forth fluidly in between those two. Just like we can, when I say square to x, I know that's the same as x to the 1/2, right? Okay, those are radical form, exponential form. This is logarithmic form, exponential form. They mean the same thing. Log base 3 of y, of 9. Blah. Sometimes I have to actually write, okay, y equals log base 3 of 9. So I realize what that's asking for is 3 to what power equals 9. That's what this is asking. 3 to what power equals 9. This is asking 2 to what power equals 1/4. Okay, this little number down here is the base. Log base 2 of 1/4 is saying what exponent do I put on 2 to get 1/4? This is saying 1/2 to what exponent gives me 8. 4 to what exponent gives me 1/16. That's what a logarithm is asking. It's an exponent. All right, take a second and see if you can evaluate those logs. You can pause me, of course. Okay, so log base 3 of 9. 3 to what power equals 9? 2. Log base 2 of 1/4. 2 to what power equals 1/4? Well, that would be -2. 2 to the -2 equals 1/4. 1/2 to what power equals 8? -3. Since 2 to the third equals 8, 1/2 to the -3 would equal 8. And 4 to what power equals 1/16? -2. Okay. Yeah, we already did that, yes. All right. Sounds good. Let's look at the graphs again. Okay. Okay, so let's look at these graphs. Y equals e to the x. Okay, e to the x, remember e is 2.71, whatever, 2.72-ish. Okay, it's just a number. Like pi is an irrational number. Okay, so 0 still gives me 1. It's very close to 3 to the x. Okay, 0 equals 1. 1 equals e, which is 2.7-ish. -1. Okay, we have an idea what this looks like. Okay. And it has a horizontal asymptote, right, at y equals 0. And now the inverse of y equals e to the x is y equals natural log of x, because the base of natural log, remember, is e. Okay, natural log is base e. So that's going to look like 1, 0. It's going to have a vertical asymptote instead of a horizontal asymptote. Okay. And it looks like so. Analyzing it then, y equals e to the x. The domain is all reals. The range, however, look at that. What kind of y values are coming out of e to the x? All positive, 0 to infinity. The horizontal asymptote was y equals 0. the limit, as x approaches infinity of e to the x is infinity, right? And the limit, I'll write it here, the limit as x approaches negative infinity of e to the x, okay, as x was getting really small, the limit was 0. So with natural log, it's going to be reversed. The domain of the natural log is the range of e to the x. Makes sense, doesn't it? Look at the x values. I have a vertical asymptote here at x equals 0. So the smallest x could possibly be, well, it can't even be 0, but it's, it gets really close to 0. The range, however, the y values, I can go way down here, I can go way up. The range is negative infinity to infinity. Of course, because they're inverses. So the domain of e to the x is the range of the natural log of x. The range of e to the x is the domain of the natural log of x. One of them has a horizontal asymptote, the other has a vertical asymptote, and these limits are switched. The limit as x approaches infinity. As x is getting really big, so is y. That's actually not switched at all. They both go to infinity. It's just that natural log gets there slower, but the limit's still the same. And we can't say limit as x approaches negative infinity because it doesn't. It approaches 0. So for this one, for natural log, instead of saying the limit as x approaches negative infinity, we say, I'm going to go over here, okay? Limit as x approaches 0 of the natural log of x. As I approach 0, as x gets closer and closer to 0, y gets closer and closer to negative infinity. Okay? The limit as x approaches 0 of the natural log of x equals negative infinity. Okay? When we solve logarithmic equations, we just want to do something like this. Okay? We want to rewrite this as exponent. This is x to the 1/2 equals 9. Okay? X to the 1/2. Okay, so if we want to solve these equations, we rewrite them as an exponent. This is x to the 1/2 equals 9. Now I can solve that, right? That's square root of something equals 9. To undo that, I square both sides, and we say x is 81. Okay? Here, I have a log on both sides. When I have the log on both sides, the only way these are going to be equal is if 4x equals x plus 6. Okay, I love when I have a log on both sides because I basically can just drop them. Okay, subtract x, we get 3x equals 6. Divide by 3, x will equal 2. So log base 2 of, let's see, 4 times 2, 8. Log base 2 of 8, does that equal log base 2 of 8? Yeah, I think so. Okay, here we want to rewrite them, instead of rewriting a log as an exponent, we want to rewrite this exponent as a log. This is saying log base 5 of 12 equals 3 minus x, right? That's the same as 5 to the 3 minus x equals 12. Okay, so then negative x equals log base 5 of 12 minus 3. Okay, make sure that, sometimes I write that as negative 3 plus the log base 5 of 12. I don't, I subtracted 3 from both sides, and I don't want people to think you can take 12 minus 3 there. Divide everything by a negative 1, and we'll get 3 minus log base 5 of 12. I would do that on my calculator. That's just a number. Okay, let's see what well, we'll talk about how to find that later, but it's 3 minus log base 5 of 12 is the final answer to that problem. Okay, all right. We'll continue on the next video.